everybody this morning to, thanks Mark, to today's presentation hosted by the IU Working Group on Active B-type stars. Our presenter this morning is Yaël Nazé from Liège University. Yaël obtained her PhD from that same institution in March of 2004, I believe, and is currently a senior research associate FNRS at Liège within the GAF group, where she's been since 2009. You're probably all familiar with Yaël's work. She's an expert in the physics of massive stars and stellar systems. She characterizes herself as a multi-wavelength astronomer, although I suspect that most of you know her best from her work in the X-ray domain. You may not know, however, that she's done some really pioneering work in the physics of hot magnetic stars as well, and is best known as having carried out work related to magnetic O-stars in the Magellanic Clouds. She's also remarkably active in outreach with a number of recent publications in Ciel et Espace, as well as the Journal of Astronomy, History and Heritage. And I would challenge many of us to find time to publish papers in the astronomical journals as well as the related journals. So that's very impressive work. Her presentation today is entitled The Mysterious Gamma Cast Stars, and the abstract was circulated earlier. Not surprisingly, it seems like it's going to focus on their X-ray properties. But I will point out that Yaël, like any true Liègeoise, is a provisioner of excellent Belgian chocolates. She knows where to find them and how to get them at the best prices. And so with that, I'll hand over the microphone to Yaël.
Okay, thanks for the intro, Greg. I must say that one of the good points to get chocolate just got flooded last summer, and so yeah, the news are not that good for that, but there are additional chocolate factories, so if you want chocolate, of course, no problem. You can find them in Belgium and in Liège in particular. Anyway, so today the idea was not to discuss about chocolate, but about massive stars. So let me see if that works. Carol, could you confirm? That's okay?
Looks good.
Okay, thanks. So thanks for the invitation. And of course, would like to talk this time about the Gamma Cast star, some work I've done in the last years with Gregor, with Myron and Christian. I think some of them are also in the participants. And well, those objects are a little bit peculiar, but of course they are all massive. So of course we'll be talking about massive stars. So we'll remain at the top of the main sequence. I know that they do very funny things when they evolve and when they die. A lot of gravitational wave, black hole stuff. But well, let's not talk about this for now. Let's keep the focus on their life. And of course, you know that they are hot, luminous, so that they have a lot of feedback regarding, well, of course, the mechanical energy, the ionizing luminosity, but also the chemical enrichment. And all this brings, of course, the question of the stellar winds, which are very important for those stars. And if I'm talking about the stellar winds, it's because it's a very important ingredient regarding the X-ray emission of those stars. And of course, gamma cast stars, they are defined by their peculiar X-ray emission. And so to know if something is peculiar, you need first to know what is normal, right? So I would like first to go through a little bit the properties of those stars, and you will see that there is a strong link with the stellar winds. Okay, so the X-ray, the fact that those massive stars were emitting X-ray, well, it's not a new thing, right? We know that for more than 4 decades now, and In fact, it was discovered serendipitously with the Einstein telescope, and basically the idea was, well, you were looking at X-ray binaries, and sometimes there were, whoa, different stuff in the field of view. And like here, for example, the 4 dots that you can see, those are massive star in the Cygnus OB2 association, just next to an X-ray binary. And of course, well, it was not only that one, it was also in Orion, Carina, and so it became quite known that, of course, they were emitting X-ray. Why were they emitting X-ray? Well, the thing is, they have winds, and those winds are not like the winds of the low mass star, right? It's a line-driven wind, so it's an unstable process. And you get pieces of wind going at different velocities. And of course, well, if you have things that are going at different velocities, they will go collide with each other, making shocks. And if you have such shocks, you will get heated plasma. And well, in such a case, you can get X-ray emissions. And that was a basic idea. It remains the same till now. The kind of emission you get with this kind of process, it is not a black body, it is not a power law, it's optically thin thermal plasma, meaning that you will see lines, and on top of those lines, there is a small continuum, which is Bremsstrahlung. So you can see the type of line you get, it's basically hydrogen-like or helium-like ions from CNO, magnesium, silicon, neon, this kind of stuff, and of course, a lot of iron lines all over. And using those lines, and you can fit, of course, the spectrum, and you will get the temperature of the plasma. And you know that in this case, the plasma will be soft. So typically it's temperature well below 1 kV, 0.2, 0.6 kV. And the size of the line, the width of the line is directly linked to the wind expansion velocity, because it's directly born in the wind. So you have broad lines from a soft X-ray case. And another thing is that if you look at the overall flux, well, it will be proportional to the bolometric one. This was found very early after the discovery, and it remains true. So most of the stars just have this ratio between the two, which is about 10 to the minus 7. Now, another feature which is important is that this emission, if you look at the light curves, basically it's constant. So you could imagine that if you have shocks between different wind power cells, you would have variability. But if you have enough different power cells, because it's not big shells, right? It's small pieces. And if you have enough pieces colliding at random times, well, basically overall, everything will be smoothed out and you will get a constant emission. So for the moment, we don't get this type of variability. So we have very precise information on the fact that we have a lot, really a lot of clubs. Okay. So since it is linked to the wind, if you have different features in the wind, it may have an impact on the X-ray. So for example, we had detected modulation of the X-ray flux, which occur with the same period as the pulsation in at least 2 stars, or for the moment only 2. And you can imagine that the pulsation of the photosphere drive some wind features, and then of course kind of add a perturbation over this embedded wind shock process. And another thing that may happen, you know, that many stars, they show DAX, and this is probably related to the coordinating interaction region. And well, in a few cases, we could look at the optical UV and X-ray information together. And we saw that, again, the modulation were occurring together. So we have several pieces of information like that. The thing to remember is that in both cases, this occurs in the soft X-ray range. It's definitely something related to this warm plasma, so not that hot plasma. and that the amplitude of modulation is quite limited. So we're talking about up to 20% maximum. Okay, so well, more in line with what Greg is doing is the fact that some of those massive stars are strongly magnetic, so they have large-scale, typically dipolar magnetic fields. And in this case, in addition to the embedded wind shocks, what will happen is that you will have the wind flows that will be channeled by the magnetic field and collide at the equator. The post-shock plasma, in this case, will remain more or less stationary. So in this case, you have X-ray lines also, but more narrow than you had before. And this is indeed what is observed. You have, of course, an additional source of X-ray, so that means that your X-ray luminosity will increase somewhat. And if you look, for example, here, so it is a set of binaries, and you can see, for example, this one, number 10, is a very weakly magnetic O star, so meaning that basically you don't care about the magnetic field in this one, so it has no impact on the X-ray emission. That's a typical embedded wind shock emission. So you have here, and then on top of that, you can see that the others, well, they are a little bit more brighter. It's not a huge increase, but it's less than a factor of 10, but still it's a definite increase. And so you can see that you can reach nearly 10 to the minus 6 in the helix over L-Ball ratio. The temperature of such object will also be slightly larger, at least in some cases. So you may have plasma reaching a few keV temperature. And on top of that, because those stars are often magnetic oblique rotators, you would have the rotation axis and the rotational axis and magnetic axis, which are not aligned, and therefore you will have changes with the rotational phase, changes on the angle of view. You will have eclipses of the hot plasma and so on, and so you will have flux which is modulated by the orbital period. In one case, which is a very highly magnetic NGC 1624-2, well, in this case, you also have modulation of the absorption, which is seen with the rotational phase. This was, of course, if you have a single star, but you know that massive stars, they very rarely are alone. And if you have two massive stars, basically you have two winds, so those winds can collide. And such wind collision have provided signatures that you can be seen from radio to gamma ray energies. The thing is, if you take one specific collision, it may not be seen from radio to gamma rays, but signatures of different colliding winds have been seen from one to the other. So if you take the X-ray range, basically the first observation of the massive stars that I showed you like 4 decades ago, basically they were from colliding wind binaries because they are brighter than usual, but with time, it became obvious that, in fact, not all binaries are X-ray bright. So the X-ray bright colliding winds are very rare. Then, of course, it's a little bit like for the confined wind. If you have those colliding winds, in addition to the embedded wind shock, well, you have an additional source of X-ray, so your X-ray luminosity will increase. And again, since it is a face-on collision, at least at the apex, so on the line of center joining the two star, you will have an increase in temperature. Again, it's a few keV typically. What is also seen is that, well, this emission, it's an extended emission, usually in the form of kind of a cone. And then, of course, that gives specific signatures that can be seen. And for example, if you take the helium-like ions, they have triplets line, and from them you can find where the X-ray emission comes from, and those triplets tells you that it is quite, those X-rays are formed quite far from the surface of the stars. So it's slightly different from what is seen from confined winds or for embedded wind shocks, for example. But the main thing with colliding winds, really the typical feature of those cases, is that they have variation with the orbital phase. Those changes can come from changes in intrinsic flux if you have eccentric binaries, and it also comes from different absorption because you have two stars with two different winds and you see the collision through one or the other wind. So of course you will get absorption modulation. All this can go, of course, with a lot of difficulties, but and in any case, the bottom line is really that you have phase log variation in such cases. Now, the example I've shown mostly were for O star and a little bit of Wolf-Rayet stars, and you may wonder, okay, but if I focus on the B star, what's happening? Meaning that you will have embedded wind shocks, and the pulsation case, for example, is also detected for the B stars. You will have confined winds, usually less bright, less hot than in the case of the O stars. What is not detected yet is the system and modulation linked to co-rotating interaction regions. This is not yet found for B stars. If you go to the late type B stars, well, in this case, of course, the wind is so small, so tenuous that we don't expect anything. It's a little bit like the A stars. And usually when you see something, it has the typical characteristic of PMS emission. So the usual conclusion is that it comes from an unseen PMS companion and not really the late type B star. Now, this is all well, but of course there is an exception. And that exception is, of course, the one I mentioned in the title, which is gamma gas. So I'm pretty sure that all of you have already seen it in the sky because you cannot miss it. But it's a very important star, of course, especially because it was the defining case for the PE category. So at the end of the 19th century, the Balmer lines were in emission were discovered for this case. And well, it became a kind of prototype. But about a century after this discovery, the X-ray were observed. And then there was a problem. There was a problem because, of course, the X-ray emission itself, well, it was bright, but really bright, meaning much brighter than the usual OB star, even considering confined winds and colliding winds and whatever. It was in fact intermediate between those normal OB star and the high mass X-ray binaries. But there was another thing is that it was hard. Optically thin thermal plasma as usual, but hot, much hotter than previously. So for gamma gas, the temperature, the associated plasma temperature is about 13 keV. And then, of course, since gamma gas is close and nearby and bright, well, you can look at it in details. And if you look at the light curve, well, the light curve is truly varying a lot. And it varies a lot, even on very short time scale. So a few seconds for the shortest time scale. So to have this kind of flaring behavior with such a short time scales, that means that you need a high density for the plasma. Something also quite untypical is that next to the iron complex near 6.7 keV, you had a fluorescent line of iron. And that was totally atypical compared to other cases where you could see the ionized iron lines. And you could say that, of course, the disk is playing a role here in the birth of this fluorescence line. And finally, since it was an optically thin thermal plasma, you could analyze lines. And again, from the helium-like ions, if you analyze the triplets, the ratio between the triplet lines, you can find that they are born in a place where there is either a high density or a close UV sources, or a mix of the two. That happens in the 70s. And of course, well, with time, a few other cases came by, meaning that gamma cast was not a lone bird. There were several other gamma cast-like objects. Usually it was from serendipitous discovery, but with time, of course, people tried to make a few dedicated searches. So you could take the problem in two directions. So either you take a bunch of BE star and you try to see what their X-ray emission look like, or you go in the other direction, you have unidentified hard X-ray sources and you try to find the counterpart and see if it is a BE star. And using all this, we finally arrive at current time at 25 gamma cast analogs, which are known. So it may not look that big, a number, but it's not negligible at all. In fact, if you look at it, knowing that not every BE star in the galaxy have been observed in X-ray, that means that actually the incidence rate, we cannot know it with precision, but we know that it's larger, for example, than that for the X-ray binaries. So it's not a negligible fraction, of course, of the BE category. So for the moment, what do we have as criteria if ever you want to look at your favorite BE star in X-ray? So basically, the two main criteria are the brightness and the hardness, which are the things that are easiest, of course, to evaluate. So if you take, for example, the spectra here, you can see zeta Fuki at the bottom and zeta off. Well, you can see that it drops very rapidly with growing energy. Rather different is the behavior of gamma cast with a high energy tail and the iron complex, which is quite prominent. And other cases here, also gamma cast objects do have this tail. I mean, this tail is something which is pretty obvious when you get it. So hardness and brightness are usually sufficient. And each time you have enough photons, you can go into the details. Look, for example, at this fluorescence line next to the iron complex. If you have a good light curve and you see the flaring, for the moment, each time we could go deeper, and definitely we had the same characteristic as gamma cast. Okay, so now we have all those stars. Of course, there are two main questions. The first one is that, okay, those gamma cast stars, they are all BE stars, but not all BE stars are showing the gamma cast characteristic. And so the question is why, of course, do they have something special, something that the other do not have? And in parallel, of course, you could ask where the X-rays are coming from. And in particular, what is the link with the disk? Because if they are BE stars, you expect that there is a link with the disk. We have tried to find answers to these questions. And I would say that the first thing we tried was trying to find something special, right? And we begin by looking at the photometric variability. So for example, we look at P Aquarius. We had 7 years of photometry by SMAY. And what we see in the frequency spectrum is that we do have high frequency signals. The strongest one is the strongest two ones, because there are too close. Things are close to 12 cycles a day. But of course, over 7 years, many things happens, as usual with BE stars. And you can see here we had 2 outbursts and we had changes in the frequency spectrum. That's something pretty obvious here. You can see also the signals at 12 per day, which is decreasing at some point. So yeah, we do not have the same signal to noise for all the different time intervals, but still you can see there are changes definitely in the frequency spectrum. At least for P Aquarius, we could get spectroscopic campaigns. And if you look at the spectroscopic campaigns, actually, you can see that there are also variation in the line profiles, and the frequency is the same as in the photometry, so 12 per day, the main signals. And the amplitude is quite similar in 2006 and 2019, despite the fact that the emission in H alpha was very different between those 2 years. So different state, but still very similar frequency properties. So we did a similar thing with BZ crew. So BZ crew, we had SMAY, we had BRIGHT, and we had TESS. Of course, not the same coverage, the temporal coverage for those 3 satellites. But in any case, we could look at the frequency spectrum. And again, there was a high frequency, near 9 per day, 9 cycles per day. We had also some spectroscopic data, but yeah, well, small scale changes, sure, but not really a period that could be identified for this case. Okay, that makes 2. 2 with high frequency signal, you know, it could be a weird case, who knows? So we try to enlarge the sample, and we use a test photometry to have light curves for additional stars, so 15 other gamma K stars. They are all here, and you have in addition BZ crew, which is here, which is reproduced again. So you can see the different stuff showing in the light curve. So the red noise, frequency groups, coherent signal dominating the light curve, stuff like that. And of course, it's only, all in all, it's just 17 objects, right? So it's small number statistics. But nevertheless, we can try to compare to what is seen with other set of massive stars. So we have long-term variations. Having long-term variation is not unexpected for BE stars, and the variation of the frequency spectrum with those long-term variation are not unexpected either. So it's not specific to the gamma K objects. If you look at the red noise properties, well, basically the red noise properties were in line with those of OB stars. So again, nothing special here. If you compare with the, for example, the occurrence of frequency groups in gamma K star and BE stars, considering again small number statistics, it was perfectly in line. And if you look at the coherent signals, again, more or less the same fraction. The fact that some of those coherent signals were at high frequency, it's rare, but again, same proportion in BE star and gamma K star. So we could not find anything specific, right? They just look like usual BE stars. Okay, so we tried to look at something else, and this will be linked, of course, to the origin of this X-ray emission. So basically, the scenarios that have been proposed to explain that are in 2 categories. One category says that basically it's a companion which is responsible for the emission. So it could be a compact object like a white dwarf or a neutron star, but in a very specific state. And those compact objects would simply accrete material from the disk and the wind, possibly, of the BE star. Another possibility is to have a strict star companion quite hot with the wind, and then this wind would collide with the disk of the BE star. Another set of scenarios, of course, consider only the BE star. The companion could be there, but play no role. And in this case, the idea is that you have interactions between the star and the disk through small-scale magnetic fields. And well, you can see here that the question of those stars having companions and what is the nature of the companion is quite important. So that's why we tried to look at two of them, Gamma Cas itself and P Aquarius, were known binaries for quite a long time. I put more or less here the latest reference for the orbital solutions. But not much was known for the other ones, the other Gamma Cas stars. So we did the spectroscopic monitoring for 16 other Gamma Cas stars. Now 16 plus 2 is 18, and we have 25 cases. So we have some left. And this is just simply because of the brightness. They are too faint to be monitored very easily for the moment. So yeah, well, it's not because we didn't want to follow those one. It's really that they cannot be done easily for the moment. So what did we find? We found that, in fact, we could get orbital solution for 6 Gamma Cas objects. So they have low amplitude radial velocity variation with periods which are several months. You can see this 4 cases here. We even have among those one which is a potential quadruple system, and that is not unheard of, or again among the BE stars. In addition to that, we have 5 cases where we do see radial velocity shifts, but we could not identify the periods yet. So we hope in the near future to have them. It's just a question of accumulating enough data. And so if you look at the spectroscopic binaries we found among the Gamma Cas stars, and you compare to the spectroscopic binaries from the other BE stars, well, you can see that there are often quite common features, so low eccentricity, periods which are not days, but rather weeks, months, and of course, the low mass companions, because the amplitudes are often very, very low. So again, if you look at that, there is nothing special regarding the Gamma Cas star and the other BE stars. If you take Gamma Cas itself, it's about 1 solar mass companion. You can also see that from the masses, they cannot be all neutron stars. I mean, neutron star is not the best way to explain all of them, because neutron stars should be a little bit more massive than that. Okay, so what else? I mentioned that the fact that all the Gamma Cas stars were BE stars, so they have disk and they have this peculiar X-ray emission. So the question of the link with the disk is important, but as you know, so this may disappear or be built again, and so it varies. And so the next idea was to follow, in fact, several of those stars and try to see if and if the X-ray emission was changing. So we did optical and X-ray monitoring. So for example, if you take HD 45314, which we follow, as you can see, for quite a long time now, we have equivalent with variation for the H alpha line. We have changes in the V magnitude. And because of those detected variation, we triggered 3 observations. So the first one is an observation which was taken when, well, it was a base level, basically, so meaning a dense disk, not as extreme as here in 2002, but still, you know, quite a dense and good disk. Then we had a second second X-ray observation when there was a drop in equivalent width. This drop does not mean that the emission had disappeared. Actually, what happened is that it is a shell phase. So the emission is quite strong, but there is a strong absorption too. And so basically the equivalent width decreased because of that. And finally, the last X-ray observation was taken during, again, a drop in equivalent width, but this time it was truly the wall emission that was really, really small and nearly disappearing. So you can see below the X-ray spectrum. So you have the first two, which show beautifully this iron line complex and a high energy tail. But then you have the last spectrum, and the last spectrum is much softer, much less brighter. In fact, if you look at it, AG45314 just get out of the gamma cast domain. So it lost its gamma cast characteristics. We also look at P Aquarius over time. So if you take the last decade, you can see on top right that the emission is quite changed. In fact, in early 2014, the emission nearly disappeared. And then since then it has increased, and it's still increasing for the moment. Of course, since you have a lot of spectra, you can try to look at the disk itself, and you can do tomography. So this tomography is shown below. So there are two things which are apparent. The first one is if you look at the hole. So the hole is slowly decreasing and then disappearing. So this hole, the size of this hole, when it decreases, that means that in fact the edge of the disk goes to smaller and smaller velocities, so goes more distant from the star. So that means that the disk was getting larger. And this is confirmed if you look at the top right figure by the distance between the two peaks of the profile, because the two peaks were quite separated in 2013, 2014, and then if you go to 2018, they are much closer to each other. So we do have a real big change in the size of the disk. And on the other hand, if you look at the tomography, you can also see that the disk is much more symmetric today. In fact, the V over R modulation that was seen a lot in the past has now disappeared for P Aquarius. In 2018, we obtained X-ray observation during 3 consecutive orbits of this system. And we tried to look if there were any orbital phasing. You can see the result on the image. Basically, we have no correlation between the X-ray flux, soft, hard, or even the properties like absorption, for example. We do not have any correlation with phase. We do not have any correlation of the change in equivalent with end phase, orbital phase either. And if you take just the equivalent with and the X-ray flux, you do not have any direct correlation between the two again. But of course, the system has been observed twice in the X-ray range. So for our campaign here in 2018, but also a decade before, where here you have the XMM observation, and you can see that at the time, the equivalent width was much smaller. It is at a time where the emission was getting smaller and smaller and on the edge of disappearance. So we have a difference in equivalent width between those two times. We have a difference in the V magnitude between those two cases. The star is brighter because of the disk is stronger at the time of the swift observation. And if we compare the average X-ray flux, the average X-ray flux is about 50% larger in the swift data set compared to the XMM data set. It's also slightly harder. And the absorption column is slightly larger too. However, if you take the range covered by the short-term variation in the X-ray range, well, basically the differences are not there, just because, of course, you have a whole set of short-term variation, and you have huge variations. So the range of variation is more or less the same at the 2 times. What is important to note is that at the time of the X-ray XMM observation, so this was really limited, at least as traced by the equivalent width of H alpha, but the star was clearly a gamma cast. So there was no disappearance of the gamma cast character. And then, of course, there is gamma cast itself. So gamma cast itself has been monitored for a very long time in the optical, and you can see here the evolution of the equivalent width in black from Polman paper, Polman recent paper 2021, if I remember well. Then you have here the V magnitude, so the crosses are the AFSO measurements, and the blue ones come from APT data. So you can see you do have variation on the long terms. Oops. And of course, we have X-ray observation on top of that. So at the bottom of this, you can see the lines which are, so the darker blue is for Eric's TE data, and the light blue is for MAXI data. And if you compare this hard X-ray light curve, and each point is a yearly average corresponding to the observing season of the V magnitude, well, you can see that basically you have quite a good correlation between the two. But recently you had this big increase in equivalent width, and we were a little bit curious to see if you could see any change in the X-ray range because of this increase in equivalent width. You have to note that there is no change in the V magnitude at the time, but the disk was much larger. So let's try to see, and then we had for XMM data, which can be seen here, and you do have change, that's true. Now, if you look, the maximum value of those changes does not come from the hard band, but from the soft band. In fact, what happens is that you have an absorbing event. In fact, in the light curve of gamma cast with time, several times, it was found that there was sometimes an increase in the absorption, and therefore a dip in the soft X-ray flux. This could be more or less long, and the longest events were about 10 kiloseconds, which is typically the time of the duration of our exposures. And it's just an extreme case, but it's not unheard of. So yeah, just absorbing event, nothing really specific happened to the hard X-ray range. We tried to correlate all those X-ray data with orbital phases. Nothing could come from that. We try also to correlate with the equivalent width, but again, really no obvious correlation between the X-ray flux and the equivalent width. So finally, the last two that we monitored, those were two cases where we saw a decrease in the emission line. So if you take HD 119.682, so you can see the decrease here in the data, and then you can see that there were some slight surge in the emission, but basically the equivalent width remains quite low, and we had 4 observations. 2 of them were taken when the equivalent width was positive, meaning that the line was in absorption, right? And well, what do those 4 data say? Well, We do have slight changes in the X-ray flux, but basically the hardness ratio is constant. And despite the fact that we have very low equivalent with the gamma gas character was still present each time. For V767, more or less the same thing. So we had a decrease in equivalent width, and then, well, it was a little bit more complicated. Going up and down a little bit between -2 and -4 in equivalent width. And then recently, so it has gone down last summer, early summer. And then suddenly in early July, you had this increase in the equivalent width. And so we decided to trigger again an X-ray campaign to see if we could see something. One thing again to show is that when those equivalent widths were changing, well, basically the broadband photometry was again absolutely unchanged. But anyway, on the X-ray side, well, again, despite the fact that the equivalent width was low, we still have the gamma gas character present at all time. And the X-ray flux and hardness ratio, basically they remain similar, and we do not have significant changes. Everything is within 2 sigma. So we do not have any reaction to that decrease or that flaring activity. So if I have to summarize all this, well, I could say that, okay, I hope I have convinced you that we have a subgroup of the B star, which display very bright, very hard, and very specifically varying X-ray emission, and they are named after their prototypes. Those are called the gamma gas objects. If you look into the photometry and if you look into the multiplicity, well, you do find companions, you do find some variability, but basically it's quite similar to the other B stars. So there is nothing really specific to those gamma gas objects. If you go to the X-ray and optical monitoring, so when the disk is changing, you do see also changes in the X-ray flux. But there is no clear and direct link between the equivalent width of H alpha and the X-ray flux, or between the X-ray flux and the orbital period. And in fact, the gamma gas character itself remains even when the equivalent width of H alpha is very low. That has a consequence, meaning that if the equivalent width is quite low, then you would have some I would say small disk. And so if you have a distant companion, well, it will have more difficulties to have some material flowing to that companion. So it would be much more difficult to explain to have still the gamma gas character in this area, in this case. And in parallel, you can see that sometimes the equivalent width varies, but you do not see anything changing in the broadband photometry. And the broadband photometry probes more inner part of the disk. And in such cases, what you see usually is that you don't have any change in the X-ray flux. When you have change in the equivalent width and the broadband photometry, then you have change in the X-ray flux. So it seems to suggest that the source of X-ray comes from the inner part of the width and not the external ones. And of course, we are not finished yet. I cannot present that we have solved everything and find what was the mystery about those gamma gas stars. And so for the future, there are still many things to do. For example, pinpoint exactly what are the incidence rate of those objects. And for that, we need, of course, to try to do clean X-ray statistics. So we are doing that right now. In addition, you can try to look at the lines more closely, especially the iron lines, because the line profile will change, of course, depending on where the cool material is and where the X-ray source is compared to the cool material. And so those are also things that have been done. And we hope at some point to have a real diskless event and have those stars with nothing around them and to see what happens to the X-ray emission in those cases. Okay, that's all what I had to say for now. regarding
Thanks, Yaël.
gamma cast stars.
A really lovely piece of detective work, so extensive. I'm going to open the floor to what I am sure are going to be some very incisive questions. If you could please raise your hand using the raise hand feature. I see some clapping. Or if you can't find the raise hand feature, just make yourself visible. Hub, you are number one. Please take it away. You're muted, sir.
Yeah, you're muted.
Well, then I repeat what I said. It was a wonderful overview. Thank you very much. I was very intrigued by one particular aspect of HD 45314, this campaign, that you said that at some point it disappeared in the X-ray diagram from the Kamakas group. Yes, that actually implies that there could be many more BE stars which are not yet in that regime, so that your statistics is an sure lower limit. Is that correct?
Yes, yes, of course. Since we have not yet observed all the BE stars, and since in addition, when you observe them, they are in their state, right? And they could be in another state at another time. So if the gamma cast character is varying, and in some cases is disappearing, yes, you could miss some gamma cast objects. I must, however, say one thing. HD 45314 is an OE star.
Yes.
Yeah, it is the earliest gamma cast star. And if you take the other cases where you have drops in the equivalent width which are even larger than that, you do not see the gamma cast character disappearing. So it may be specific to the fact that it is an E star and that the cleaning is going faster. If you remember the papers done by Asif and Dylan Key, so the temperature of the high temperature of the O star may play a role here.
Yes, did you mention that Zeta of UV is also one of them? In the very
first... No. I was showing the spectrum of Zeta of UK because it was different of the others.
Okay.
It's not of them at all.
Yeah. And the other point was the fact that that you did not find anything special about the binary characteristic of Kamakas itself, yeah, and the phenomenon. Wouldn't that imply that the binarity perhaps has nothing to do with it?
That's indeed a possibility, of course. Yeah.
Okay. Well, thank you so much. I enjoyed it thoroughly.
Thanks, Hud. Norbert, you are next up. Please go ahead.
Great. Yeah, well, thanks very much. Really nice talk. Fascinating objects. Interesting questions in the background. So I have a few loose thoughts and questions. So first, the binary incidence. So you looked at a sample of the Kamakas stars and found a certain fraction of them can be detected as binaries. Does that mean that the binary incidence is high? I mean, in the sense, could you repeat that experiment with an average BE star, you know, of similar mass? I guess you have to do the same, keep the same mass range. And would you expect a similar binary fraction?
Yes. In fact, binary incidence amongst the BE stars has already been studied in several ways. And if you take, for example, some recent papers like those by Clement and others, you will see that basically people are more and more going into the direction that all BE star could be binaries. And of course, we could say the same for the gamma gas stars. In fact, for some of them, we have clear binary signatures, and for others, actually, it's difficult to say if they are binaries or not because they have so much change. The lines, because of the disk has so much change between the different spectra, it's very difficult to make sense of radial velocity shifts for those ones. So yes, they could all be binaries, the gamma gas star or the BE. That's the way the data are going to.
So for the, say, more massive part of the BE stars, the early B-type stars, perhaps, I think most people would not expect all of them to be binaries because if their companion was massive enough to produce a neutron star, then the chance that the binary has broken up in the supernova explosion is very large. So that's why
Because at least some of them remain together because we have the BE X-ray binaries, right?
Yeah, sure. Some remain together, but we know for the kicks the neutron stars get that most of them should not. And then to understand what the companions are in the gamma gas stars which you see, it is, of course, as you pointed out correctly, very important to get an idea about their masses. And so I understand that you well, you see radial velocity variations, so they are basically SB1 systems, right? So you get from that, I would expect if you have the orbital solution, you get a strict lower limit on the companion mass. It seems that you have other ways as well to constrain the masses of your companions, but I didn't quite understand how you did that. So,
okay,
so which ways can there be to get further constraints?
Okay, from the mass function, you have to choose the inclination, of course, if you want to be more precise with the secondary mass estimate. So for the SB1, there are cases where you do see lines from, well, something linked to the companion, like in the Bjorkman study of P Aquarius, or if you take for gamma gas, the inclination is quite well known. So for those one, we know the mass more or less with certainty. For the other ones, we can have reasonable range of inclination. Those are B stars. They cannot be seen just pull on because you wouldn't see those broad lines, of course. And a last thing is try to get the SB2. And this is something that will be done soon.
Okay, so you have the hope to see the companion, really.
Yes.
That would be indeed tremendous. Thank you.
Thanks, Norbert. So that brings us to the end of our time. It's 10 o'clock. I'd like to thank Yaël again for an excellent talk, really enjoyable. And Carol, do we have any information about our next presentation in this series?
So it'll be on the same third Wednesday of the month. And I believe, though I'm just trying to confirm, I think it'll be Catalina Arcos from Chile will talk to us then. So
most excellent. All right, and there are thank yous and congratulations in the chat. Thanks very much, everyone. Wishing you a good beginning or end to your day, depending on where you are, and looking forward to seeing you in a month's time. And maybe some of you in Leuven in July for the TaskCask meeting.
Hey, thank you.
Thanks for organizing this. It was great.
thanks, Yaël.
Bye, everyone.
Bye-bye.
Bye.
Bye.